Welcome to the video series on Scilab and XCOS tutorials. So the last time we explored generating a sine function, and this video will mainly be about exploring trigonometric entities, mainly sine and cosine functions, and seeing their convolution, their addition, their products, and thereof. So much like the last video, let's go to sources and import two GenSine blocks. Right. Uh, from sources, we'll also need a clock because it's a continuous time values. Uh, we take a C scope for visualizing the output. And for the moment, right. So let's take care of our GenSine functions. Let's say we want one with a magnitude of 10 and frequency. Let's go with our assumed one by 100th. Sorry. Yep. And keep it phase 0, which is a typical sine wave. Similarly for this one, let's keep this one's magnitude a little higher, let's say 20. Same frequency because it makes it easier to analyze. And phase, let's also give it a sine wave for now. Right. So if I want to watch these two waves as they evolve together, what should I do? As we've discussed earlier, we go to signal routing and we insert a mux block right here. So this function goes to the first port, this one goes to the second port, and the mux outputs to the C scope. Now, before we run the simulation, we need to decide how long to run the simulation for. So for our case, our angular frequency is 0.01 radian per second. So one full cycle will be 2 pi by this value of omega. So if we want to run it for 2 cycles, it will be 4 pi by omega. So 4 pi is roughly around 12.56, and that into 100 as it's divided by 0.01, it's 1256. So let's go to C scope and change our refresh period to 1256 because this is the amount of time it will wait before refreshing its buffer. And the same needs to be done for simulation setup and change the final integration time to 1256. Okay, so Control A, click O on your keyboard to optimize the lines, and then our code's good to run. Click on reframe to contents. So as we can see, we have two sine curves in phase with each other, but differing in their magnitudes. So this is just the basics of what I wanted to talk to you about. Now let's just say that the 21 is displaced where angle of pi. So if it is displaced by pi, then it is absolutely out of phase. It is destructive phase in nature, this wave. So let's see how that's going to be plotted. They are completely going to be opposites of each other in polar. Yeah. So you see, they are in phase, but exactly 180 degrees apart. So they are the opposites of each other as far as directions are concerned. So that's one. And also, if we want to plot a cosine wave with this, let's say the magnitude 20 wave will be a cosine wave. So a cosine wave is displaced from a sine wave by 90 degrees or pi by 2. So if we plot that, the 20 magnitude one will be a cosine curve. You can see that, right? So it's 1 at the 0 value, and it's 90 degrees out of phase with the sine value. So the last thing that I wanted to represent before ending this video is how to represent a three-phase electrical power system. So for that, we're going to need another block. So we're just going to copy this block. For three-phase electrical power, each phase carries the same power. So I'll keep everyone's magnitude equal to 10. And each of them are displaced from each other by 2 pi by 3. 2 into, right, 4 pi by 3, right? So we also need to change the number of input ports in our mux, change it to 3, and we get this one right over here. Control A, optimize, and let's run the system. Oh gosh, wait a second. I think we haven't changed the magnitude of this one yet. Right. Now let's run the simulation. It should give us a three-phase sine power curve, and that is exactly how it looks. So, so now you see how we can use the sine generator function to generate different functions of a sinusoidal nature. So this is going to be very useful when we study Fourier analysis or power systems in general. So this is one of the most common curves found in power systems engineering, mainly because most of our power that we use is three-phase AC power. So we'll be going over a few more applications of the sine waves in the next video, but I hope you found this useful. Thank you.